Hey, welcome back to your favorite pre-calculus class. We're gonna take a look at the version B on this. If you want to follow along here, let's take a look at this first one. We've got log base 2 of x plus 5 plus log base 2 of 2x minus 5 equals 3. We're going to go ahead and condense these first using the product rule. So we've got log base 2 of x plus 5 times 2x minus 5 equals 3. So we'll condense it into one logarithm. Then we're going to go ahead and undo it with its inverse. So I go 2 to this side, 2 to that side, and that'll bring down the x plus 5 times 2x minus 5 equals 2 to the third. 2 times 2 times 2 is 8. Now we're going ahead and solving this quadratic. So I got 2x squared minus 5x plus 10x minus 25 equals 8. I'm going to get one side equal to 0. So we've got 2x squared, combine those, plus 5x minus 33 equals 0. So that'll factor into, looks like I'll have to have 2x and x, and that'll factor into plus 11 minus 3. Check that real quick. Yep, that works. So we got 2x plus 11 equals 0. X minus 3 equals 0. Add 3 over here. Subtract 11 and divide by 2. So I got negative 11 halves. Go ahead and check those back into the original. If you notice, if you plug in negative 11 halves plus 5, well, negative 11 over 2 plus 10 over 2 is negative a half. So I have log base 2 of negative a half plus, I'm not even going to check the rest of it because I can't have a logarithm of a negative number. So I've got to throw that out. So I just have x equaling 3 would be the only one that would work on that one. Let's look at number 2 now. We've got an exponential. 3 to the 1 minus 2x minus 21 equals 6. First of all, I'm going to isolate my exponential. I'm going to add 21 to both sides. Now I'm looking at that 27 and I'm thinking, can I write that as 3 to the something? Well, sure. 3 to the third is 27. So now I have the same base on those. So I know my exponents. I can set my exponents equal to each other. And if you want to be technically proper about that, we'll go ahead and run log base 3 on both sides. But either way, it'll bring down the 1 minus 2x and bring down log base 3 of 3 to 3 is 3. And then we'll go ahead and solve that. So we got negative 2x equals 2. Divide both sides by negative 2. So we've got x being negative 1. We can go ahead and check that into the original problem there, and we'll see that that'll work out. All right, number 3b here, we've got e to the x equals 4.5. I'm going to go ahead and undo e with the natural log. ln of e to the x is x, so I got x equals the natural log of 4.5. Now I'm going to pull up our decimals, round that to 4 decimal places. Notice here we got 1.50407, so let's go ahead and write that down. 504077397. Now we're going to round this to 4 decimal places, so that 7 to the right is going to bump that up. So that's all right, we're still solving a polynomial inequality. Make sure you got one side that's the 0. Looks like you do. You got 4x minus x squared. What we're finding here is our critical point. So we're going to go ahead and factor that. We're going to imagine it's equal to 0 for a minute, right? Imagine it's equal to 0. So that would mean x equals 0, 4 minus x equals 0 would be our critical point. So x equaling 4 and 0. That would be on my testing interval, 0 and 4, right? Now I got to decide, do I include them or not? Well, if I throw in x equaling 0 into the original, I would have 0 minus 0 squared is 0 less than 0. No, it's not. I'm not going to include those because this is a strictly less than situation. So I'm not going to include either of those zeros, right? Let's plug the 4 in. If I plug 4 in, I got 4 times 4 minus 4 squared. Is that less than 0? 16 minus 16, no. 0 is not less than 0. Again, it's a strictly less than, so those are not going to be included. So I leave those as an open hole is how I like to do that. And then I'm going to test something to the left of 0. I'm going to test something between 0 and 4. And I'm going to test something to the right of 4. Let's throw in -1. So I got 4 times -1 minus -1 squared. Is that less than 0? I got -4 minus 1 is -5 less than 0. That is true, right? I get a negative answer. That's true. So that's going to be part of my solution. So my open interval is from negative infinity up until 0, and it spit out a negative value there, right? Now I'm going to test something between 0 and 4. So let's test between 0 and 4. And let's plug that in. So I got 4 times 1. I'm testing 1. Minus 1 squared. So I got 4 minus 1 is 3. Is 3 less than 0? No, it's not. So that's not going to be part of my solution because it spit out, in this case, a positive 3. All right, so that spit out a positive value there. Now let's plug in something to the right of 4. So this is now the interval from 4 on. And let's test 5. So I got 4 times 5 minus 5 squared. Is that less than 0? 20 minus 25 is a -5. Is -5 less than 0? Yes, it is, right? It spit out a -5, spit out a negative, which a negative number, of course, is less than 0. So our solution set is this true part, right? From negative infinity up to 0. And this other part that ended up being true that spit out a negative value from 4 to infinity. And that would be our solution set for 4b. First thing I'd be checking is make sure you got these vertical asymptotes, -4 and 1. Oops. -4 and 1. -4 and 1. That one's okay. -4, 1. That one's okay. -4, 1. That one's okay. It looks like all of them have -4 and 1. Let's check the horizontal asymptote y equals 0. Well, this one has y equals 1, so that one's out. The next one has y equals -1, so that one's out. So it looks like C and D could be it because they both have y equaling 0 as a horizontal asymptote. So let's now check the x-intercept, -3/2, 0. So -1.50, looks like that one has it. And let's check D, -1.50. Okay, that one's okay. And now I'm just going to check, how about 0, -3/8. 0, whoops, that's not it. That's a positive, I don't know what that is. Positive 3/8, that's the wrong y-intercept. So it's got to be this one here, 0, -3/8 right there. That looks like that's the right one. So it looks like we'll graph D on this one. All right, on 6b, it looks like we have these characteristics. Use the information to choose the correct graph here as well. First thing I'm looking at is my zeros. Actually, you know what? The first thing I'm going to look at is this power function. It's an odd degree, so it's either going to behave like x cubed with a positive leading coefficient, or if the leading coefficient's negative, it'll go up to the left, down to the right. Well, the leading coefficient is a positive 3/2, so it's got to go down to the left and up to the right. So A is okay, B is okay, C is out. That goes the wrong way. The end behavior is wrong, and so is D. D is out. The end behavior is wrong on those two. So I know it's got to be either A or B. Now let's go ahead and try the zeros. The first one has a 0 of -3 with multiplicity 3. Well, this is an odd multiplicity, so it's got to cross through at -3. Let's check the first graph. See how it crosses through at -3? Over here at -3 on graph B, it just touches it. So I know B is out. Let's just check the final 0 here. It has a 0 of 1 with multiplicity 2. It's an even multiplicity, so it's just going to touch it right there. See how it just barely touches the x-axis right there. So it looks like it's got to be graph A here for 6b, problem 6b. 7b, we've got f minus g of 2. Now remember, f minus g of x is just f of x minus g of x, right? So f minus g of x, if I was doing that, would just be f of x minus g of x. So we'd have f of x minus g of x, which is 5 minus 3x. Notice I put that in parentheses because I've got two terms there. Well, if I'm finding f minus g of 2, then I'm just plugging a 2 in for the x. So we got 30 over 2 plus the 2 cubed minus 5 minus 3 times the 2. All right, we're plugging 2 in. So f of 2 minus g of 2. That's all we're doing here. So I got 20 over 2 plus 2 cubed is 8 minus 5 minus 6. So I got 20 over 10 minus a negative 1. So I got 2 plus a 1. It looks like I end up with 3. On this one. Oh, I'm sorry. That's not 20. That's 30. I don't know why I changed that. Whoops. That's a 3 plus 1, which ends up being a 4. How bad. We got the difference quotient here. Now, if I'm finding f of x plus h, what you have, here's our f of x. If I'm plugging in x plus h in for x, then I've got x plus h in there, all right? And that, of course, will distribute there to that. So there's our f of x plus h. Let's go ahead and put that in over here. F of x plus h, so x plus h is going in for f of x, or for x, so x plus h going in for x. Okay, there's f of x plus h, minus the original f of x. Well, the original f of x is 3x squared minus x over 5. And this is all over h. So we just got to clean this up. So we got 3x plus h, x plus h, minus that x plus h all over 5, minus 3x squared plus the x over 5. This is all over h. And what I'm going to do is I'm going to get this all over 5. Right now these are over 1, so I can get this to be one fraction right there. So let's go ahead and multiply by 5 and 5. Multiply this by 5 and 5. And so we've got 15, x plus h, x plus h. That'll give me x squared plus xh plus hx, so 2xh plus h squared. That's expanded x plus h, x plus h. Minus x, minus h. These are all over 5. Minus 15x squared over 5, and plus x over 5. And this is all over h. So we've got 15x squared plus 30xh plus 15h squared minus x minus h minus 15x squared plus x. This is all over 5. And this is all over h. Well, now I've got a fraction over a fraction, h over 1. So I can multiply by 1 over h here. And so I've just got 5h in my denominator. So I got 15x squared minus 15x squared, that's gone. 30xh plus 15h squared. Notice the minus x and the plus x, that's gone. I've got minus h, and this is all over that 5h. Now I want to factor out an h out of the top so I can cancel with the bottom. So I got 30x plus 15h minus 1. This is all over 5h. So now my h's cancel right there. So I've got 30x over 5, 15h over 5, minus 1 over 5. So 6x plus 3h minus 1/5 would be our difference quotient for this one. Here we've got a piecewise defined function, 9b. We're finding f of 5. So then I got to say to myself, is 5 less than 0? No, it's not. Not that one. Is 5, less than 3? Oh, where'd that go? Is 5 less than 3 and greater than or equal to 0? No, it's not. Not that one. Is 5 greater than or equal to 3? Yes, it is. So I'm using f of x equals negative x minus 3 because 5 is greater than or equal to 3. So plug it in. I got negative 5 minus 3. Looks like I got negative 8. There's my answer for that one. Now the second one says, what's f of 0? Well, is 0 less than 0? No, it's not. Is 0 less than 3 greater than or equal to 0? Yes, it is. So I'm using that second one. F of x equals negative 4. Plug the 0 at least when it's less than 3 greater than or equal to 0. Plug in the 0. Well, there's nowhere to plug the 0 in for x. It's just negative 4. Now I'm going to plug in f of negative 3. Is negative 3 less than 0? Yes, it is. So I'm using the f of x equals the absolute value of x because negative 3 is less than, is less than 0. Absolute value of negative 3 is 3. So there we go on that one. All right, this time we're asked to use the graph to find what are the intervals of increasing. Where are we increasing? Where are we going up and to the right if x1 is less than x2? Where is f of x1 less than f of x2? Hopefully you can see on that interval up until negative 6, we are increasing on that. And then do you have any other areas where you're going up and to the right as you read it left or right? Well, they're in red you do, so you name it also in terms of the x values from an x value of negative 1 up until an x value of 0. That's your intervals of increasing. Remember, those are always open-ended intervals. As we're looking at where are we decreasing, so where am I going down and to the right? Do I have anywhere that I'm going down and to the right on this one? And you say, sure. Only right here from negative 6 x value to negative 4. That's the only place I'm going down to the right. In other words, if x1 is less than x2, f of x1 is greater than f of x2. Right? That's your formal definition for decreasing. Now, where are we constant at? The only place where we're constant, where f of x1 equals f of x2, is on that interval from 0. Oops, almost missed this other one over here in orange. Let me do that one first. The interval from an x value of negative 4 up until an x value of negative 1, and then also the interval that starts at 0 in orange there and goes on. That's where we are constant on this graph. All right, this one here we've got a function. It's a third root, third power polynomial here, and it looks like it has a 0 at 4/3, right? So let's go ahead and write it. I got 27x to the third squared. And if 4/3 is a 0, then we know x minus 4/3 is a factor. And so we're going to go ahead and go to the side. I say 4/3 is a 0. And I'm going to divide that. 27x cubed minus 54x squared plus 27x minus 4. Looks like I have no placeholders needed. I don't need to put any zeros in. I have all those terms there. I know it's a 0. They already told me it's a 0, so I know I'm going to have no remainder here, or I did something wrong, right? So I know it goes in cleanly. Drop the 27 down. 27 times 4/3 looks like I get 36. I got negative 54 plus 36. What's that? Negative 18, I think. Negative 18 times 4/3. I think that's negative 24. 27 minus 24 is a 3. 3 times 4/3 is 12/3 or 4. Negative 4 plus 4 is 0. So it looks like it'll be 27, 1 degree less, x squared minus 18x plus 3. Let's go ahead and put it in over here. 27x squared minus 18x plus 3. Now notice on this 27x squared minus 18x plus 3, notice I could take a 3 out of each of those. And in fact, I'm gonna multiply that through because that'll make that into just an integer coordinate here. So I'm sorry, it'll give me integers here as my coefficient of x and as my constant term. 3 times negative 4/3 is just a minus 4. So I got 3x minus 4 times 9x squared minus 2x plus 1. And again, notice that still gives us the 4/3 as our 0. That's why I did that. It just is a little cleaner look there. But I've got a quadratic at this point, so I'm going to go ahead and factor my 9x squared minus 2x minus 1. I'm going to guess it's probably 3x and 3x. It could be 9x and 1x, but let's try 3x and 3x. And let's see if that would be 1 and 1. It's either got to be plus, plus, or minus. Minus. Whoops, I took a 3 out. My goodness, what did I do on this? That's supposed to be... I made an error right there, you guys. I'm sorry, that's a 6. Whoops. There we go, and it does factor. Good grief. So 3x minus 1 times 3x minus 1. So my zeros, if I was setting this equals 0, right, would be the 4/3 and 1/3 with multiplicity 2, which means it just touches it right there. So our answer here, the other zeros, of course we have the 4/3, but that's already listed. What they want here is the other zeros here, the 1/3 and 1/3. Well, if I'm looking at this, I don't see like a coefficient of 1 on either of these equations, so I'm going to just say, let's just do elimination. Or linear combination method. And I'd probably get rid of the y's. You could get rid of the x's if you wanted. So the least common multiple of 3 and 2, right? I'm looking at the 3 and the 2 is 6. So if I multiply the top by 2, notice I'll have 8x minus 6y. So I need the bottom one to be a positive 6y. Well, it's already a positive 2y, so I just need to multiply by 3. And then I'll have 18, and this is both sides of the equation. And notice it's gone. There, my y's are gone, right? Negative 6y plus 6y. I got 18x plus 8x, so I got 26x equals 13. I divide both sides by 26, so 13 over 26, and I get x equaling a half. And so now I know x is a half, and since these are both linear equations, I can just pick one of the equations, doesn't matter which one it is, and plug it in. So I got 4 over 2 is just 2 minus 3y equals 5. I subtract 2. I get negative 3y equals 3. Divide by negative 3. I get y. 3 over negative 3 is negative 1. So it looks like we end up with the point 1/2 negative 1 is our x and y coordinate there. If I'm looking at this rational function f of x, we got x minus 4 over x squared minus 9. I'm thinking to myself, well, for a rational function, where is this thing undefined? What causes this thing to be undefined? Well, let me factor this difference of squares. And I'm like, oh yeah, I can't have a 3 and I can't have a negative 3 because I'll be dividing by 0 on this, right? So my domain would be x such that x is all real numbers, but I can't be negative 3 or 3. But we're putting this in interval notation. This is set notation. Let's put it in interval notation. Anything up until negative 3, and then we'll go between negative 3 and 3, and then anything after 3. Again, remember the interruptions here are at negative 3 and 3. If I'm looking at this next one, I've got g of x, I've got an 8x minus 3, but I've got a square root. Well, that kind of throws a wrench in things, because with a square root, remember, I can only take square root of, and we're taking the domain and the real numbers. I can only take a square root of things that are greater than or equal to 0. So normally, I would say greater than or equal to 0, because I can take the square root of 0. But this thing is in my denominator, so I cannot be 0. Right? So I'm going to take out the 0, right? I have to be my radicand there, that 11 minus 5x, because it's in a denominator, actually has to be greater than 0, so that I'm not dividing this whole thing by 0. And then let's go ahead and solve that. I get negative 5x greater than negative 11, divide by negative 5. Now, remember, when I divide by negative 5, that's going to switch the sense of my inequality. So I'm less than 11/5. Anything less than 11/5. So negative infinity up until 11/5, but again, cannot be 11/5 on that, because that'll make it undefined. All right, number 14 here, we've got this rational function, f of x equals x plus 1 over 4 minus x. Find the intercept. So if you remember, when we're finding our x-intercept, we always let y be 0. To find our y-intercept, we're going to let x be 0. So let's go ahead and find our x-intercept here by letting y be 0. That's our f of x. Well, we know if we have the top of this, if the top of this is 0, 0 over 4 minus x is always 0, right? So the top of this makes this true. So we have 0 equaling x plus 1. So we just solve that for x. We get x being negative 1. So there's our x-intercept is negative 1, 0, right? If we were graphing that, we'd throw that on our graph, right? Our y-intercept, now we're going to let x be 0. So f of 0, we're going to let x be 0, 0 plus 1 over 4 minus 0. So f of 0 equals 1 over 4. So when x is 0, y is 1/4. So we got 0, and we're 1/4 of the way up there. Now let's find our intercepts, or I'm sorry, our asymptotes. So here's our function f of x equals x plus 1 over 4 minus x. To find our vertical asymptotes, this is where is this thing undefined? Well, it's wherever our denominator is equal to 0. It's going to make this undefined, right? We cannot divide by 0. So I'm going to go ahead and add x to both sides. And it looks like our vertical asymptote ends up being x equaling 4 is our vertical asymptote. Now remember, we're never going to cross x equaling 4, right? Because that thing makes it undefined. We can't have a value of x being 4. Now for our horizontal asymptote, I'm looking at this function, x, or this rational function, x plus 1 over 4 minus x. Now notice it's 4 minus x instead of negative x plus 4, right? I want to write that in standard form on the bottom there. And that's because I want to look at the degree of the top. The degree of the top is 1. The degree of the bottom is 1. If you remember those rules, when the degree of the top equals the degree of the bottom, right, then we take the leading coefficients. Well, the leading coefficients is 1 over negative 1. It's automatically the leading coefficients, a to the m over b to the n, or whatever our coefficients were when we wrote those rules. So y equals negative 1 would be our horizontal asymptote, y equaling negative 1. So I'm going to go ahead and draw that. I mean, I know we don't have to graph this, of course, but it's kind of nice to make it visual. So y equals negative 1. Now, just as a reminder on the horizontal asymptote, if the degree of the top, let's say the degree of the top is 2, the degree of the bottom is 1. If the degree of the top, I can't remember if I used m or n, but if the degree of the top is more than the bottom, then there's no horizontal asymptote. There's the potential for an oblique asymptote, and you would have to do the division to do that. If the degree of the top is less than the bottom, so like let's say the bottom was x cubed, right? The degree of the top is less than the bottom. You know what? Now that I think about it, I think I used n and m. So sorry about mixing those up. I think I used n for the degree of the top and m for the bottom. But anyways, if the degree of the top is less than the bottom, it's automatically y equals 0. And it was those 3 rules to find our horizontal asymptotes. Oops. Now, this one's, part 3 is asking, find the range. So you're thinking, well, what's the range of this thing? What's my set of y values? Well, you've already got a couple over here. You could plug some more in, and what you're going to kind of see is that, right? So again, I'd plug in a few more points. I'd probably plug in a few points to the right of this as well. And what you're going to see is that that thing is actually down below that y equaling 1. So it's kind of like this. Now the question is, do I actually hit this horizontal asymptote? Like, do I actually ever, like, maybe I didn't know what it looked like. I hadn't plotted points. Like, maybe does it go up and actually cross right here at negative 1 and then approach it as it goes out, right? that could have, you could have some weird stuff with a horizontal asymptote. Remember, you can cross it. So how do you check that? Well, my functional value f of x is x plus 1 over 4 minus x. Does it ever hit a y value of negative 1? And so you just got to solve that and see if that's possible. Do you ever hit that? Well, what I'm going to do is I'm going to multiply both sides by this 4 minus x. Get that on the top, 4 minus x, and multiply it by that negative 1. So then what we have here is we got 4 minus x times negative 1, so negative 4 plus x equals x plus 1. And if you notice when I subtract, when I solve for x, get all my x's on one side, oh, they're gone. I have negative 4 equaling 1. Does negative 4 equal 1? No, it doesn't. That's false. So you are not going to hit a y value of negative 1. You're never going to hit that horizontal asymptote, right? And so it was a better graph before, because if you would have plugged in like 5 or some other points and you'd plug them in, and you just want to check, you know, if I plug in 5 for x, where's it at? I got 6 over negative 1, so I got negative 6. So 5, I'm down here, negative 6. Anyways, you could plug some more in, and you'd see that it's down there below that. That's that rational function. So our range is coming from negative infinity, does not hit negative 1, but then it takes off again after that, right? So coming from negative infinity up to negative 1, I never touch that horizontal asymptote. Then I take off again after that, and I keep going up with my y values. I know this question doesn't ask for the domain, but let's go ahead and just address the domain on this function here. Remember, you never cross that vertical asymptote, that green vertical asymptote at x equaling 4. But notice we hit all these x values, we stop at 4, don't hit 4, and then we take off again after 4, right? So in this case, our domain would be negative infinity up to 4, and then we'd take off again after 4 would be our domain on this one. All right, this problem is asking for this polynomial that's right now it's in factored form. What would the leading term be? Like if we multiplied this thing out, right, we have 4x, we had x minus 5, x minus 5, x minus 5. Oh man, I didn't leave enough room. Anyways, there's a bunch of these x minus, there's 6 of these things, right? 1, 2, 3, 4, 6. Anyways, we started multiplying these and blah, blah, blah. Anyways, what would that first term be? Well, it'll be 4x, and then there's x minus 5 to the 6. So that one would be x to the 6 times that 4x in front. So 4x to the 7th. And I don't know why I wrote 4. 7. Plus blah, 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 right? If we were to expand that. So what's our leading term? Y equals 4x to the 7th. What is that degree? Well, the degree, of course, is 7. So if the degree is odd, now it's asking us a question about the end behavior, right? So if the degree is odd, does it behave like x cubed, which goes down to the left, up to the right, if the leading coefficient is positive? Or if the leading coefficient is negative, does it go up to the left, down to the right, like negative x cubed does, right? Well, this one has a positive leading coefficient, so I know it's the one that goes down to the left, up to the right. So let's see if we can't select the correct statement. So as we follow this thing to the left, again, I don't know what it does in the middle here, but as we follow it to the left, as x goes left, notice the y is going down. The y is going down. Now over here on the right, as we follow x to the right, as we shoot to infinity, as it increases in magnitude, the y also increases in magnitude. It shoots up, right? As x goes right, y shoots up. As we follow it to the right, y shoots up, right? So we're looking for the one that has those two statements on there. Looks like that would be D here. As x goes left, y goes down. As x goes to the right, y y goes up. All right, part 4 here. Find the y-intercept of the graph. Well, the y-intercept would be, let me go ahead and write this, y equals 4x, x minus 5 to the 6. The y-intercept is where your x value is 0. So we got 4 times 0, 0, 0 minus 5 to the 6. Well, 0 times anything is still 0. So the ordered pair would be 0, 0. And just for end behavior, remember if you would have had like let's say you had a different function, like let's say negative 2x to the 6 plus blah, blah, blah. Now the degree is even. So if it's even, it's either going to go up and up like x squared with the leading coefficient positive, or if the leading coefficient's negative, it's going to go down and down. And in this case, the leading coefficient's negative, so it would have been that one, right? So just remember your end behavior, depending on the degree being even or odd, and the leading coefficient. All right, 16b here says we're trying to find the equation of a line is perpendicular to this given 2x minus 3y equals 4. In fact, let's make this visual and take a look at what this looks like here. Divide everybody by negative 3. So it looks like I've got a slope of 2/3, a y-intercept of negative 4/3. So if I was graphing this, I'm down 1 1/3. Negative 4/3 is my y-intercept, and then I have a slope of 2/3. So I'm up 2, right 3, up 2, and right 1, 2, 3. And we could kind of draw. All right, so here's the given line. Now what they want is they want the equation that goes through negative 2, 5, but it's got to be perpendicular, right? So we're looking for that red equation here. Well, we need two things to write the equation of a line. We need a point, which we do have a point that on that red line, negative 2, 5, but we also need a slope. Well, since it's perpendicular, we steal the slope from the given equation. We say, well, the slope of this blue line, this slope is 2/3. So we know, number one, that the perpendicular slope would be the opposite reciprocal. So we flip that around instead of 2/3, 3/2, and we change the sign, negative 3/2. So we know the slope of the red line has got to be negative 3/2 because it's perpendicular to the blue line. And we know it goes through negative 2, 5. So there's my x1 and y1. And so now we just go ahead and we plug it into the point slope form. Y minus y1 equals m, negative 3/2 x minus the negative 2. So we got y minus 5 equals negative 3/2 times x. Negative 3/2 times a positive 2, negative 2, is a negative 6/2 or a minus 3. And now we're going to add 5 to both sides. So we got y equals negative 3/2 x plus 2. That's the equation of that red line. All right, 17b here, we've got a function given, a graph, visual. It says find f of 2. What's the functional value when x is 2? So I'm going to go over to when x is 2. I'm going to find the point on the graph there, put the dot on there. It looks like f of 2 ends up being negative 4. When x is 2, the y value is negative 4 right there, functional value. So what are the solutions to f of x equaling 0? Well, when y equals 0, that's my x-intercepts, right? When my y value is 0. So it looks like I hit right there at 2 spots. Negative 2, when x is negative 2, I have a y that's 0. And when x is 1, I also have a y value that is 0. And what about a relative minimum? Well, a relative minimum would be the lowest point in an area, so it's like bottom of a valley type of deal. So this would be our relative minimum. So the relative min is negative 4. It occurs at an x value of negative 1. But they want the coordinate here, so we'll just go ahead and punch it in as a coordinate for the solution. -1, 4 is your relative min. And of course, this one over here, that would be our relative max. That would be the top of the hill right there. Nice spot in an area. That would be a relative max over there. But they didn't ask about it on this one. All right, so the graph here looks like we've got a quadratic given. So does it have a minimum or maximum? Well, this thing opens up, so we obviously have a minimum right there. So we have a min, right? We have a min on this. What is the min value? It looks like it's -3. Min value, the y value of -3. By the way, all right, that's where the lowest y value it has is. What's our vertex? Well, if I'm naming that as a coordinate, I want to name that, it looks like it's -3 is the x, and we know the y is already -3, right? Our vertex is where this minimum is at, right? So either the bottom of the quadratic, or if it's flipped over, it'd be the top of a quadratic, the vertex point, right? Axis of symmetry goes right through the vertex, so that's that vertical line, x being -3. That's our axis of symmetry, x being -3 there. Our domain for a quadratic function, it's going to be defined everywhere, so all real numbers. The range, though, here you notice that the range is starting off at that y value of -3, and then it goes up, right? So take off from -3, and then it goes up for our y values, and we do include that -3. Right, now write the function's equation in that form. That's our vertex form. So what we have is, we have our vertex hk. That's the -3, -3. That's our hk. We know that a is positive because it opens up, but we don't know what the value of a is yet. So we're just going to have to use another point on there. So I would pick a nice and easy point to plug in, like maybe one of these intercepts, like either 0, 0, or looks like -6, 0 is another one you could use, but I would use an xy point. How about, let's try the -6, 0. Let's use that xy. So I'm going to use that and solve. I'm going to solve for a using my vertex form equation with my hk and my xy. So my y is 0. A I don't know. My x is -6. I use the point -6, 0. Minus my hk. Remember, h is -3. And k is -3. See how we have hk, x, and y there? And we can solve for a. So we got 0 equals a. -6 plus 3 is a -3 squared. Plus a -3, so -3. 0 equals a times 9 minus 3. Let me add 3 to both sides. So 3 equals 9a. Divide by 9. 3/9 is 1/3. So now we know a is a third. So now we have our vertex hk, and we know that a is 1/3. So y equals, or I should say f of x. I was erasing that. F of x equals a, x minus h squared plus k. Our a here is a third, x minus h plus k. And there's our vertex form. That's the equation for this graph. Now if I'm looking at this composite function, right, they're asking us f of g of x, right? Like if this is our original h of x, who's the g of x that's going in as the input into f? I always like to make it whatever's quote on the inside, if you will. Like if I have a radical, I'll probably make it the radicand, right? So I would make that g of x my 2 minus 3x. All right, so this is f of 2 minus 3x. Well, if 2 minus 3x becomes my input, then what would f of x be? Well, f of x would have to be the 2 minus 3x is my input. So that 2 minus 3x, the stuff underneath the radical, is my input x, right? So my f of x would be 9 root x. And of course, if you're not sure, you can always check it using f of x and g of x. F of g of x, check your work here. That would be f of my g of x I'm claiming to be 2 minus 3x. Now I'm using my f of x, which is 9 root x. And who goes in as the input x? 2 minus 3x. There's the original. So I know that'll work out for this one, right? So you're looking for your f and your g on this. Thanks so much for watching and taking notes on version B. We'll see you next time.